requirements that generate a design that allows me to have compartmented information on my network. Does everybody on the network have a need to know all the information that's on the network? Chances are the answer is no, and so you have to have some kind of requirements defined that allow you to design in the need-to-know information. In this phase of the system engineering lifecycle, you start to identify what your threat is and assess the vulnerability that you have to that threat and the vectors by which that threat may be realized. So who are your adversaries? What are their motivations? What are their capabilities? And how are they going to get to you? If you've got a large wireless system, that has one set of vulnerabilities and provides one set of vectors. An entirely wired system, no wireless, has another set. Yeah. Now I can take the approach that I'm going to mitigate all possible vulnerabilities in my system before I let it operate. How long do you think it'll be before that system comes online if I have to mitigate all vulnerabilities? Yeah, you grin. That's the answer. It never will come online. So we take a risk management approach. We mitigate that which we can mitigate easily. We have to assess things that the expense of how expensive it's going to be versus the actual cost of what the cost of the breach might be. So I don't want to spend $600,000 to fix a vulnerability that the worst case is might be $10,000 of damage. Where we draw the line is an important consideration. So in vulnerability assessment, we have to identify the components of our system and assess each of those, the paths that can result in the security breach. And at the end of it, we have to be able to present to the customer what his level of risk is now that we've mitigated all these vulnerabilities. So he has to specifically state that he is accepting the residual risk in the system before it can get the authority to operate. So if you're a system security engineer, you can see that a lot of your time is spent in the front end of a program. And most people find this probably the least interesting part. And the most interesting part is the design phase, which is, in my experience in designing systems, is the shortest period of time in the design, in the delivery of a system, is in the design phase. But I agree it's probably one of the more interesting pieces. My experience is as a system architect, and so I find myself in the front end and in the beginning of this phase, and then usually by the middle of this phase and the end of this phase, I'm off to another program. But as a software engineer or a hardware engineer, this is where you get to strut your stuff. Before, you were trying to figure out what it is you were going to do. Now that you've got the plan, you've got the preliminary design, and now it's time to finish that design and get to the critical design review, which is often the gate whereby we come out of the design phase and into the implementation phase. So we're going to start doing some software development here of modules. We're going to start performing the more interesting pieces of risk and vulnerability assessment. This is where we start using tools to scan things, where we start working with the vendors to understand what their vulnerabilities are. You're going to start making some trades here on what products to bring in if you're using what's called commercial off-the-shelf or COTS, or free and open source software, FOSS. If you end up working with government contractors, you'll hear those terms a lot. So the security architecture for a system presents a lot of different kinds of views of what the system is going to look like. So you're going to have an overview of the entire system that's going to give a pretty picture for the customer. He's going to be able to look at it and goes, I understand what it is that I've asked for, and I understand how we're going to get there at a very high level. And then I start having other views that derive from that, the network security view. So I may have an architecture view of a bunch of boxes on a page that is my network for this particular system, and then I've got a security view of that network. I've got another one for the operating systems, perhaps one for the applications, one for the database. I may have a data flow diagrams as part of my architecture, and that's one of the views that becomes very important in the implementation phase, hardware view. But sometimes we have system operations views as well. But this cost effectiveness becomes a hard problem, one that is not easily solved and probably never will be. How do you determine when something is cost effective? It's pretty hard in the information security world to prove that you've done a good job, because you've done a good job if nobody has made it in, but maybe nobody's made it into your system because nobody's interested, and you've got a lot of vulnerabilities. So how do you measure this? What's the probability of breach? What's the cost of data revelation? So if my data gets out, what kind of cost does that have to my organization or to my customer's organization? How much is it going to cost him to recreate data that is destroyed? How much did it cost him to develop that intellectual property that he's now lost? That becomes part of the cost factor here. If it's privacy data, or in the case of like TJ Maxx, it's credit card data, they've got a lot of legal costs that they incur because of that breach. And some of those may be catastrophic costs if the shareholders decide to sue because they have not performed the due diligence necessary to operate a system. And you balance all that sort of thing with the cost of protection, the impact of performance, and so on. And again, know the acceptable risk rather than striving for mitigating all possible risk to zero. One of the concepts that had a lot of input years ago, and I guess we talk about it less now than we used to, is the trusted computing base. That's the components of the system that we know something about. We know how much we can trust we can place in them. And these are the components in the system where we want to do the most valuable work. So if I've got a distributed system and part of it operates in the cloud, part of it operates privately, what do I want to do in the cloud and what do I want to do where my trusted computing base is unknown versus what I want to do locally where I have some control over the trusted computing base. Do I need to, in order to protect the things that I'm trying to protect, do I need to actually develop something myself, or can I go out and find it? Or can I adapt something that is already made to do the job for me? And then how much assurance do I have to put in things? So the next phase in the system engineering lifecycle is implementation and test. So here's where we start doing things like testing for functionality. So we have to generate our test plans, our test processes, we have to conduct the tests, we actually have to figure out how we're going to conduct them and if the conduct of the test is sufficient to get me an answer that I'm looking for. How do I report the discrepancies that I've found? And then how are those discrepancies fixed? So, who fixes them? How does it get back into the system engineers, the software engineers, hardware engineers, to get a workable solution back into test? And then you may have accreditation testing, which is kind of the opposite of functionality testing. Functionality testing, you test something to prove that it does what it's supposed to do. In accreditation testing and security testing, you actually are trying to devise tests to prove that it doesn't do what it isn't supposed to do. And if I have a system that's got 14 million lines of code, how long do you think it's going to take me to exhaustively test that system? Will I ever get done? No. So my test procedures and my test plans have to, and my test engineers have to understand what's important and how do I test to make sure that what's important is tested. And then it goes back to the vulnerability and threat analysis that I did earlier. I've identified the vectors by which an adversary may attack my system. Now I need to test to make sure that I've blocked those vectors in some effective fashion. Have I made it so expensive for him to be able to breach my system that he's going to go to somebody else? He's going to spend his time on somebody else and not me. It's the same kind of thing as running from a bear. If you're faster than your companion, you've got it made. This is the stage in which it gets the most attention from the certification and accreditation activities and the formal security evaluation. But you can see from the design here that this extends all the way back into the beginning of the phase. So here is the culmination of the work that you started in the security requirements phase of your life cycle. You will do another risk and vulnerability assessment at this point. Now what you're looking for is, were the risks and vulnerabilities that you tested for or that you looked for before fixed, but are there new ones? So a year ago you started your system development on Ubuntu 13. And today, Ubuntu is up to 16, and they've done a number of patches. Is your residual risk and vulnerability assessment the same as it was under a previous version? So if you're all Linux and you're all doing it as a Linux, your entire project is Linux, that's one set of calculations. If your project is Windows,